All right, welcome back to our second day of digital lectures. Hopefully, things are going okay so far. As a reminder, please reach out to me by email if you have anything specific about your situation that makes any of this online learning stuff exceptionally difficult. I'm more than happy to work with you. Also, more than happy to give exceptions and extensions to things this week while we're still adjusting to our new workflow here. Just a couple quick reminders. Quiz 8 is due today, so is homework 24. Those were originally due on Monday, but were extended until today to give people a little extra time to adjust. Homework 25 is also due today. It is Wednesday. I'm speaking as though it is the date up here that this lecture will appear, not the date it actually is, so ignore this March 24th up here. I'm pretending it's March 25th. So tomorrow, March 26th, Thursday, labs are due by 5 p.m. So make sure you have those in. As a reminder, you can complete your labs anytime between Monday at noon and Thursday at 5 p.m. They are designed to take about 3 hours each, just like the regular labs, but it's okay if you go over this time. You are also allowed to talk to other students about the lab as long as you are always doing your own work and not just copy pasting other people's spreadsheets or data. One of your classmates mentioned something that could be useful, and I want all of your opinions on it. And it is kind of an office hour Zoom meeting. Apparently, some other classes are having at least an hour or so a week where the professor is just there on Zoom, and as much of the class as wants to be there can join so they can all ask questions and hear the answers the instructor gives all in one location. I'm open to doing something like this. I'm a little leery of it because of the time zone difference many students will be facing, but if we can make it work and make it fair for everybody, I'm more than happy to do that. So please chime in the thread on Piazza about your thoughts on the different ways we could run a Zoom office hour meeting. As a reminder, again, I am also available just about any time of any day for a one-on-one meeting on Zoom. Just send me an email and we'll set something up. So, with all of that out of the way, we are now ready to actually start material for today. So today we're talking about magnetic induction, Faraday's law, and Lenz's law. And really, both Faraday's law and Lenz's law are aspects of magnetic induction. So induction is our primary topic for today. And the discovery of induction can be explained, at least in terms of the phenomenon itself, by a pretty simple observation. And that is, if you move a magnet around near a coil of wire, a current will flow in the loop of wire. Or in the coil, as I've called it. But if the magnet is held stationary, nothing happens, no current flows. And this is kind of fundamentally, at least in a conceptual point of view, what magnetic induction is. Here we have a magnetic effect causing an electric effect. By moving the magnet around near a coil of wire, we induce a current in that wire. There are many connections between electric fields and magnetic fields, not least of which is one we've already learned with Biot-Savart law, that moving charges, currents, an electric effect, cause magnetic fields. And this is kind of the reverse of that, where a magnetic field can then cause an electric effect, or a specific kind of magnetic field. Now for a more formal statement of magnetic induction. A changing magnetic flux through a loop of wire or a coil of wire does what we call induces an EMF in that coil of wire. So, to kind of elaborate on what I mean by this, let's imagine we just have a loop of wire. Literally just one piece of wire, and we twisted it into a circle and tied it off at the end, so it's all electrically connected. And we are going to do something by moving around a magnet, maybe turning up the strength of our magnet, maybe moving it closer to this loop of wire, something that is going to change the total amount of magnetic field that's going through this loop, or the magnetic flux. And if we have a situation like this, then basically the wire is going to act like it has a battery attached. I am going to put quotes around this battery. Probably not a very formal practice for diagrams, but I want you to remember that this battery is not actually here in the loop of wire. The wire is just acting as though it has a battery attached to it while the magnetic flux is changing. And the voltage of this battery is the induced EMF. As far as the orientation of this battery, which side of the battery has the positive side or which side of the battery is the negative side, whether current will flow clockwise or counterclockwise, that's actually what we're going to need Lenz's law for. This statement in red here is Faraday's law, at least in words form. And we will get to a mathematical statement of that soon enough. But you probably heard a word in this explanation that you remember. You probably heard the word flux. And if you're thinking back to flux and remembering the last time that came up when we talked about Gauss's law and we found the electric flux. This time we're finding the magnetic flux, but it's the same idea, and you calculate it much the same way. So the magnetic flux is the integral over some closed three-dimensional surface. Well, it doesn't have to be closed, actually. But over some surface of B dot n hat times dA, which we sometimes wrote in a slightly different way, where we just let dA be a vector, where the direction of dA was the direction of that normal vector. And one last version of this formula that we could have is the magnitude of B times the magnitude of A times cosine of theta. And you can only use this last definition if the magnetic field, magnitude and direction, is uniform across the whole loop. So, just to remind ourselves what these terms are, let's draw ourselves a loop of wire that I'll draw here in gray. This loop of wire will have a normal vector. And that normal vector will be perpendicular to the loop itself. I missed my chalkboard dotted lines. And then the magnetic field will be passing through this loop in some way. Maybe it comes in this direction. So all of this is magnetic field. So in this case, if our normal vector points this way, perpendicularly up out of the loop, and our magnetic field is pointing this direction at the place we've drawn our normal, then the angle we want for this equation, I'm trying to use good colors. I've heard reports that the green is not easily visible. This angle right here between the normal and the magnetic field is your angle theta up here. Now note that we're not going to have closed surfaces with Faraday's law like we did with Gauss's law. With a closed surface, you always pick the outward-facing normal, but with a loop of wire, you can pick whichever normal you want. So there's nothing stopping you from picking the normal that points down this way instead, and in this case, this angle would be theta. So that orange theta goes with the pink normal vector, the green theta goes with the green normal vector. Whichever one you do, just pick a direction for your normal vector and stay consistent the whole time, and you'll be okay. So, now for the actual formal statement of Faraday's law. This is mathematically Faraday's law. The induced EMF is equal to the negative rate in change of the magnetic flux over time. Or, in a certain circumstance, we might end up multiplying this by n, and I'll explain what that is in just a second. This does not need to be here. There we go. Where to define a couple of these variables, n is the number of loops in the wire. So if you imagine a solenoid, and you guys can Google that real quick if you need to, just a bunch of loops of wire, you get credit for the magnetic flux going through each of those loops, even if it's all caused by the same magnetic field. So anytime we have a derivative, we can rewrite our equation with deltas instead, as long as we remember that this is not exactly the same equation. It tells us something similar, but not the same as the other equation. This will tell us the average EMF induced over a certain interval of time. But if we want to know what's happening at a specific instant, and the magnetic flux is changing at some nonlinear rate, we will need to take a derivative here. So there is an important question that comes up here. And let's say you do this calculation and you get a positive value for our induced EMF. Now in our loop where we have current flowing, and we'll draw current in orange here, well, does a positive EMF mean our imaginary battery is oriented like this and current flows clockwise? Or does a positive EMF mean our imaginary battery points the other way and current flows counterclockwise? Which direction around a circle is positive? Well, it kind of depends from which side of the circle you're looking at. So the easier way to keep track of this, rather than trying to make sure you're looking from the appropriate side of the circle and remembering whether counterclockwise is positive or negative, is that instead of trying to answer this question this way, we will use Lenz's law. So in short, Faraday's law will tell us the magnitude of our induced EMF and eventually our induced current. But Lenz's law will actually tell us the direction that current flows. And that's what we're going to talk about next. So Lenz's law has a formal statement here, and it is as follows. Current is induced in whatever direction it needs to be, in such a direction as to oppose the change in flux within the loop of wire. Now there's going to be a couple different magnetic fluxes here going on. There's going to be the original magnetic flux, some external magnetic field we're making stronger or weaker somehow. Then that's going to induce a current and an EMF in this wire, but moving charges then create their own magnetic field. So there's going to be a magnetic flux that I'm going to call the external flux, and then there's going to be a magnetic flux called the induced flux, which is caused by the induced current. So it will be important to keep those two separate in our minds. So I've got a few examples of this for you because it's easier, in my opinion, to figure out what's going on in a more concrete situation. So let's say we have a loop of wire, and I'm going to draw it in the final case as well. Oops. Same loop of wire. It is much harder to draw circles on this tablet than it is on a whiteboard. So to begin with, let's say there's no magnetic field at all in this region. And then afterwards, we turn on a magnetic field directed out of the board. What direction will current be induced in this loop? So we look for first the change in external flux. This B equals 0 and this B being out of the board, that is our external magnetic field, so that is the external flux. Since the external magnetic flux started off with a value of 0 because B was 0, and it ends up out of the board, that means the change in external flux is in a direction out of the board. And then we need to induce a magnetic flux to oppose this. So we will induce a magnetic flux the opposite direction, into the board. Then we need to ask ourselves, which direction of current, induced current in this loop, will give us a induced magnetic flux into the board. So think about this using your second right-hand rule, and you can check your answer here just a second. And we will find that our induced current is going to be clockwise. So when we make this change, current will flow clockwise in the loop. So let's do a couple more examples. I'm going to put them up on the board or up on the screen, and you can give them a go yourselves before checking your answers with what I'm going to write. So for situation 2 here, we're going to start off with a magnetic field into the board, and we are going to end with a magnetic field of 0. So in this situation, we've turned off the magnetic field. Okay. And the last example I'm going to do, or the last example I'm going to kind of step you through one step at a time, is to say that to begin with, let's say we have a magnetic field out of the board at 4 Tesla, and at the end, we have a magnetic field into the board at 4 Tesla. And in between here, we rotated our magnetic field by 180 degrees. This is actually very similar to what happens in motors and in generators. So think through each of these and give them a go, pause the video, and see what answers you get. So let's talk through these and see if we got the right answer. So first we need to figure out, for this second example, what the change in external flux is. Well, we started off with our flux into the board, and we ended with no flux at all. So this means the direction of the change in our flux, the important thing here, is actually out of the board. So think of this a different way. If we take out of the board as positive, we started off with a negative flux, and we ended up with zero flux. So to go from a negative number to zero was a positive change in your value. Thus, the change in external flux being out of the board. So then the next step is pretty easy. We need to induce a magnetic flux in the opposite direction, into the board. And then we figure out what direction of current this produces, and we have an induced current, again, clockwise. Note that both of these last two examples had the same answer, even though we're doing something very different between the two of them. One case we're turning on a magnetic field, but turning on a magnetic field out of the board. And the other case we're turning off a magnetic field, but turning off a magnetic field that's into the board. So how about this last one? We start off with a magnetic flux out of the board, and we end up with a magnetic flux into the board. So if we just want to know the average EMF, all we really need to know is what happens between final and initial. But we should really consider every moment in between. And I can't really draw this easily, but as the magnetic field starts to rotate, that cosine theta, I believe? Yep, that cosine theta term goes from positive 1 slowly, steadily, all the way to negative 1, if we take out of the board as positive. So that means that our change in external flux here is actually into the board, which means we need to induce a magnetic flux the opposite direction, out of the board, which means the induced current will, this case, be counterclockwise. Well, one more quick corollary question here. Let's put a final 2 on this one. And for this problem, let's let the magnetic field rotate another 180 degrees. So it goes now from into the board to out of the board at 4 Tesla. Now what's happened? Well, using our same color codes here, now we've gone from into the board to out of the board. Cosine of theta has gone from negative 1 steadily up to positive 1. Not linearly, but it never decreases. So that means our change in external flux is now out of the board, which means we have to induce a magnetic flux into the board, which means we have an induced current that is clockwise. So for the first 180 degrees, we have counterclockwise current. And the next 180 degrees, we have clockwise induced current. And if we let the magnetic field continue to rotate, we'll continue to get current that bounces between clockwise and counterclockwise, clockwise and counterclockwise, and this will be alternating current. Just to kind of give you a summary of some of this that I think helps on how you oppose different changes. there are two types of changes in the external flux you'll have to deal with. One of them is opposing an increase in the magnetic flux. The other one is to oppose a decrease in magnetic flux. And if something is increasing and you want to oppose it, you need to fight back against it. This is what we saw in our first example over here. There was no magnetic flux before, and it tried to increase. And specifically, it tried to increase in a direction out of the board. So we fought back against it. This increase was in a direction out of the board, so we induce a magnetic flux the opposite direction, into the board. Similarly, if something is decreasing and you don't want it to decrease, it needs help, it needs reinforcements. I don't know if you guys can hear my cat meowing in the background, but he's never going to shut up if I don't let him into this room. Hold on a second. What do you want? If you walk on my keyboard, I'll stab you. Yes, go look at the birds. You're in my way. So sending reinforcements, I'm back now, was what we did in example 2 right here. The magnetic flux was originally into the page, but it started to get weaker. So that means we needed to oppose this change, since the magnetic flux was into the board, but it's getting weaker. It needs help. We need to send reinforcements the same direction into the board. So this is just my little anthropomorphized way of looking at this that helps me remember it, on how to oppose the change in flux. You can also set positive and negative directions for into the board and out of the board, and work through things that way. So, with all this in mind, I want to show you guys some PhET simulations. So this one is called Faraday's Law, and it's the most relevant one, but there are another few that might be useful. Faraday's Electromagnetic Lab, Generator, and Magnets and Electromagnets could all be relevant to what we're talking about. These other 3 are still on the original Java coding, which is a slight security risk to your computer, so install it at your own risk. And I am not allowed to install it on my own computer without the permission of Brendan Post. But luckily, Faraday's Law has been updated to HTML5, so it's perfectly safe to run just on your web browser. You can see the URL up here at the top. So we have a magnet here, and a coil of wire, and a light bulb. And we'll see that if we move the magnet around near the coil of wire, we get a induced EMF. And you can see the kind of pseudo voltmeter up at the top. And we can already see a couple of things that we might have guessed from Faraday's Law. One of them is that it's the rate of change, the time derivative of the flux, that tells you how much voltage you get. So if we move this magnet slowly, we don't get very much flux at all. We get some positive in this case, negative as we're moving towards the loop, positive as we're moving away from the loop, negative moving towards. But if we move things faster, we get a larger flux. A larger induced EMF. Something that can help here is to turn on the field lines so that you can actually see what's happening. And I just want to talk you through one of these examples at least. So here, let's say we have the magnet with the north end facing the loop, and we leave it at rest, and we're going to move it closer. So as we move this magnet closer, well, we saw the voltage go into the negative, and let's see if we can figure out why that might be. What changes about the magnetic flux as I move this magnet closer? Well, the closer you are to the magnet, the stronger the magnetic field is. You can even see it. Here we have 6 of these magnetic field lines going through the loop of wire, and back here we only have 2 or 4, depending on how you count it. So we've increased the number of magnetic field lines going through the loop, or we have increased the flux through that loop, and that flux is directed to the left. So the change in external flux as I move the magnet from here to here is directed to the left through the loop. You oppose an increase by fighting against it. So that means to oppose this change right here, we need to induce current the opposite direction through this loop, or we need to induce flux the opposite direction. So to induce flux to the right through this loop, that direction, well, we would need current to come down through this wire and start looping around this way. Check this with your second right-hand rule and go back into here. And that's what you can see is that when I make this change, current flows into the negative terminal of the battery, and that's what corresponds to a negative voltage up there. So if we move the magnet in, we get a negative voltage. So I recommend playing around with this and seeing if you can explain each of the following phenomenon. One of them is, when we move the magnet closer, we get a negative voltage, but when we move the magnet further away, we get a positive voltage. See if you can explain that. Another aspect of this is if I flip the magnet around, well, now when I move it closer, I get positive, and further away, I get negative. Why is that? Another thing you can do is click this other button down here, then flip my magnet back around, and see the differences between a loop with 4 coils and a loop with 2 coils. So I'm just going to move my magnet back and forth, and you can hopefully see that I'm getting some voltage here. And if I move my magnet around the same amount on this upper loop, I don't get nearly as much voltage. I still get an induced voltage, but not nearly as much. So these are things you should all be able to explain based on what we've talked about with Faraday's law and Lenz's law. Don't forget, whatever terminal the current enters into, that is the sign of the voltage that this little digital voltmeter is reading. So fun to play around with, can give you an idea what's actually going on. But back to lecture. All we have left for today is a big long example problem, because we don't do many example problems. Now we have more time to do those. So we are going to take 40 centimeters of 2 millimeter diameter copper wire, and pull it into a circular loop. We're going to have a magnetic field with a strength of 25 millitesla that makes an angle of 20 degrees with the surface of the loop, or the plane of the loop, if you prefer. And then the change we're going to make here, because none of this does anything if the magnetic flux is not changing, we are going to turn B up, turn up the magnetic field. Maybe this is an electromagnet, and we turn up the current. And we're going to turn it up to 52 millitesla over 31 milliseconds. And I want you to find the direction and magnitude of the induced current. I highly, highly, highly recommend that you pause the video right now and try this yourself. As a reminder, you're going to need, or as a hint, you're going to need a formula from back when we first learned about resistance as part of this example. But the rest of it is all Faraday's law, Lenz's law, and yeah, just some algebra and geometry. So give this a go and see what you get, and then use my work to check your answer. This is clearly a big multiple part problem. And when I have a big multiple part problem, sometimes I like to start at the end. And one of the most common questions about physics problems, I have no idea how to start. And if you don't know what to do, start at the end. Start with what you need to find, the induced current. Do we know any formulas that can help us find the current? Well, the wording of this problem makes me think it's a magnetic induction of Faraday's law problem, so we're probably going to have an induced EMF somewhere. And we can think to ourselves, do we know any formulas that relate an EMF, which is a voltage, to a current? And we do. We have Ohm's law. So V equals IR. And we can slowly work in to figure out everything we need. If we want the current, we're going to need to calculate these other two things. And we can figure out how to do that. So first, let's figure out how the heck do we find this voltage? And then a little bit later, how the heck do we find this resistance? So this reminds me of like a video game, maybe like Animal Crossing, where they're like, we need you to go turn on the town train station. And you go to the town train station to turn it on, and they're like, well, for that to work, we need the rail pass. And then you go to somebody's house to get the rail pass, and they're like, well, for me to give you the rail pass, you're going to have to catch 47 fish or something like that. This is kind of the same idea. We know what equation we want to use at the end of the day, V equals IR, and that equation is telling us what we need to go find. It's giving us direction. In order to find, pun totally not intended, in order to find the current, we need first the voltage and the resistance. So let's find those things. So I'm going to do the resistance first. And as you might remember from way back in the day, since we weren't given our resistance values or color codes, we can default to our original formula for resistance of anything. Rho L over A, where rho is the resistivity, L is the length of whatever resistor we're talking about, and A is the cross-sectional area. So, well, I have to look up the resistivity of copper. I had to check this in a table. This is something that would be given to you on a test or a quiz, but you could look up on a homework problem. 1.68 times 10 to the negative 8th ohm meters. The length of this copper wire pulled into a loop is 0.4 meters, or 40 centimeters, but converted into SI units. And then the A here is the cross-sectional area of the wire. Well, it has a 2 millimeter diameter, so it has a 1 millimeter radius. So the area is pi times r, 0.001 meters squared. So we can plug this all into our calculators now and get a value for r of 0.00214 ohms, or 2.14 milliohms. No actual resistor has a resistance this low. We're dealing with resistors in lab that have resistances in the hundreds of thousands of ohms, and this is the contribution we're getting from wires in our circuit, something this small. So we're partway there. We've gotten the rail pass for Old Man Raccoon. I don't know, it's been a long time since I played Animal Crossing. I don't remember any of the characters' names. Tom Nook, I think, was one of them. Anyway. So we've now got R, and the only thing we're missing is V. So how are we going to find V? How do we find the voltage or potential difference that's going to be created in this circuit? Well, we still have to think a little bit. And we still have to recognize that this is a magnetic induction problem, so we're probably going to be finding the induced EMF of this loop. This V that we need is going to be the induced EMF, And the induced EMF, well, we weren't given a function for B, so I'm going to use the delta version of the formula, the change in magnetic flux over the change in time, which, well, we don't know what the change in magnetic flux is. That's going to be our next step. But we do know the change in time. The amount of time over which this happens is 0.31 seconds. Sorry, 0.031 seconds, 31 milliseconds. So I'm going to call this step up here 2, where we found the resistance. I'm going to call this step 3, where we found the formula we're going to use to find V. So now this formula, just like before, is telling us what it needs in order to proceed. I'm sorry, I know this green is bad. I'm working on getting a better color for it. Oh, there it is. Oh, there we go. Did that change that permanently? No, it didn't. Of course not. Okay, so now we have to find V, because we need V to find I. To find V, we now need the magnetic flux. So we need to find a way to find the magnetic flux. And this will be step 4. And we'll be using the formula that the magnetic flux is equal to, the simple version of the formula here for a uniform magnetic field, BA cosine theta. So let's draw a diagram here to make sure we're understanding everything. We have our loop of wire stretched into a circle. The magnetic field, which I'll draw in blue, makes an angle of 20 degrees with the surface of the loop, where this is our magnetic field. And I'm just going to go ahead and say that this goes into the page. So this is the side view where this would be the top and this would be the bottom. So when we want BA cosine theta, we can start trying to calculate that. And I'm going to need more room, so I'm going to continue this process up here. I'm sorry, I know this is a lot of arrows. So the initial magnetic flux will be the magnitude of B initially, 0.025 Tesla, times the area of this loop. Well, I don't know what that area is yet, so I'm just going to call it A. And then times cosine of whatever angle theta we need. A reminder that our normal, we can pick any one we want, so I'm going to pick the normal vector that points downward. We want the angle between the magnetic field and the normal vector. This is the theta that we need, not the 20 degrees. I do this all the time on test problems. I give you a different theta than the one you need to see if you guys actually know what that theta in that equation means. So we don't need 20 degrees here. We need 70 degrees. But we still don't have A. And similarly, we can find the final magnetic flux, which is going to be the same thing with a 0.052 Tesla times A times cosine of 70 degrees. So we've now unlocked the next stage of this journey. We need to find A. So this is not the cross-sectional area of the wire like the A we used up in this pink section was. This is this area. The entire area of the loop itself. So, well, we need to know its radius. Well, 2 pi r equals the circumference. And our circumference was 0.4 meters, so we can find the radius of this loop is 0.0637 meters. And then the area is just pi r squared, and we get 0.0127 square meters. So now we finally completed a step and we aren't missing anything. This means we're done. We just need to Dr. Seuss our way back through this complex, nested series of calculations. So we take our value for A that we found here and we plug it in for A in these equations. And that lets us calculate each of these magnetic fluxes. The initial flux was 1.086 times 10 to the negative fourth Tesla meters squared, also known as a Weber. And our final flux is 2.259 times 10 to the negative 4. Also Webers. Dude, what are you doing? That box is not for you. Sorry, cat stuff. Then we go, so we've completed this green step now. And now we take these numbers that we just found from our green step for our initial and final flux, and we are going to put them back into our formula for the induced EMF. Well, we'll keep that negative out front, but final 2.259 times 10 to the negative 4 Weber minus 0.086 times 10 to the minus 4th, again, Webers, divided by our 0.031 seconds. And we get our induced magnetic flux is, well, we get a negative 0.00378 volts. I tend to just ignore this negative sign. We're going to account for direction with Lenz's law anyway, and something being a negative voltage without really specifying a direction we're going to travel around this loop doesn't have a lot of physical meaning. And now we can take our answer for R from up here and our answer for the voltage or the induced EMF here to set up our Ohm's law calculation. 0.00378 volts equals I times 0.00214 ohms. And we can solve for our induced current as, where did I write that down? There it is, 1.77 amps. So there is the magnitude of our induced current using Faraday's law. Now we need to know Lenz's law. So, and from our top view, initially, we had a magnetic flux into the board. Oops, that is not the end of the board symbol. There we go, into the board. And afterwards, we also had a magnetic flux into the board, but it's bigger because we turned up the magnetic field. So this means our magnetic flux increased. So we need to fight back against this by inducing a flux in the opposite direction. So we need to induce a magnetic flux out of the board, which means, using our second right-hand rule, that our induced current is counterclockwise, from our top view at least. So hopefully you did pretty well on this. This would be a great question to put on like a quiz or a test, but I would have to remember when writing it that this type of question takes a lot of time. It's got a lot of moving pieces. But if you can follow this and recreate it yourself, you've got a pretty good understanding of a lot of the circuits and magnetic field stuff that we've been doing. All right. I don't think I have anything else for all of you. The next lecture will be posted on Friday. Don't forget to go comment on Piazza, letting me know what you want to do about this digital office hour and whether you'd prefer that be synchronous and available to the entire class or whether you would rather keep that as a one-on-one, just email me to make an appointment and I'll meet with you just about any time type of thing. Up to you. I just want to know what the class thinks before I make a decision. That's it for material for today. Thank you for watching, and have a good day.